Hello and welcome you guys in another session of Aditya L1 Important Facts which you must know. The Aditya L1 mission is launched by ISRO's PSLV-XL rocket from Satish Dhawan Space Center Shar, SDSC Shar, Sriharikota. Initially, the spacecraft will be placed in a low Earth orbit. Subsequently, the orbit will be made more elliptical and later the spacecraft will be launched towards the Lagrange point, L1, by using onboard propulsion. The total travel time from launch to L1 would take about 4 months for Aditya L1. PSLV C-57 is the 59th flight of PSLV and 25th mission using PSLV-XL configuration. It is planned from 2nd Launch Pad, SLP, SDSC, Shar. PSLV C-57 will launch Aditya L1 spacecraft in a highly eccentric earthbound orbit. The spacecraft will perform orbital maneuvers by using its LAM to reach Sun-Earth Lagrange point L1, 1.5 million kilometers from Earth, in a halo orbit. Major science objectives: understanding the coronal heating and solar wind acceleration, understanding initiation of coronal mass ejection (CME) flares and near-Earth space weather, to understand coupling and dynamics of the solar atmosphere, to understand solar wind distribution and temperature anisotropy. Aditya L1 is the first space-based observatory-class Indian solar mission to study the Sun. The spacecraft is planned to be placed in a halo orbit around the Lagrangian point 1, L1, of the Sun-Earth system, which is about 1.5 million km from the Earth. A satellite placed in the halo orbit around the L1 point has the major advantage of continuously viewing the Sun without any occultation eclipse. This will provide a greater advantage of observing the solar activities continuously. The spacecraft will carry 7 payloads to observe the photosphere, chromosphere, and the outermost layers of the Sun, the corona, using electromagnetic and particle detectors. Using the special vantage point of L1, 4 payloads will directly view the Sun, and the remaining 3 payloads will carry out in situ studies of particles and fields at the Lagrange point L1. The suite of Aditya L1 payloads are expected to provide most crucial information to understand the problems of coronal heating, coronal mass ejection, pre-flare and flare activities, and their characteristics, dynamics of space weather, study of the propagation of particles, fields in the interplanetary medium, etc. Uniqueness of the mission: first time spatially resolved solar disk in the near UV band. CME dynamics close to the solar disk, tilde from 1.05 solar radius, and thereby providing information in the acceleration regime of CME which is not observed consistently. Onboard intelligence to detect CMEs and solar flares for optimized observations and data volume. Directional and energy anisotropy of solar wind using multi-direction observations. Aditya L1 science payloads. The Aditya L1 mission carries a suite of 7 scientific payloads to carry out systematic study of the Sunday. The Visible Emission Line Coronagraph (VELC) studies the solar corona and dynamics of coronal mass ejections. The Solar Ultraviolet Imaging Telescope (SUIT) payload images the solar photosphere and chromosphere in near ultraviolet (UV) and also measures the solar irradiance variations in near UV. The Aditya Solar Wind Particle Experiment aspects and the Plasma Analyzer Package for Aditya (PAPA) payload study the solar wind and energetic ions, as well as their energy distribution. The Solar Low Energy X-ray Spectrometer (SOLEXS) and the High Energy L1 Orbiting X-ray Spectrometer (HL1OS) studies the X-ray flares from the Sun over a wide X-ray energy range. The Magnetometer payload is capable of measuring interplanetary magnetic fields at the L1 point. Why study Sun from space? The Sun emits radiation light in nearly all wavelengths along with various energetic particles and magnetic field. The atmosphere of the Earth as well as its magnetic field acts as a protective shield and blocks a number of harmful wavelength radiations including particles and fields. As various radiations don't reach the surface of the Earth, the instruments from the Earth will not be able to detect such radiation, and solar studies based on these radiations could not be carried out. However, such studies can be carried out by making observations from outside the Earth atmosphere i.e., from space. Similarly, to understand how the solar wind particles and magnetic field from the Sun travel through the interplanetary space, measurements are to be performed from a point which is far away from the influence of the Earth's magnetic field. Lagrange points. The Lagrange points are the portions in space where a small object tends to stay, if put there. These points in space for a two-body systems such as Sun and Earth can be used by spacecraft to remain at these positions with reduced fuel consumption. At Lagrange point, the gravitational pull of the two large bodies equals the necessary centripetal force required for a small object to move with them. For two-body gravitational systems, there are total 5 Lagrange points denoted as L1, L2, L3, L4, and L5. The Lagrange points for Sun-Earth system are shown in the figure. The Lagrange point L1 lies between Sun-Earth line. The distance of L1 from Earth is approximately 1% of the Earth's distance. Thanks for watching. If you like this video, please like, share and subscribe the channel.